Welcome to Ready to Derive. In our study of limits, you will recall that we learned about a very important property of functions, continuity, a condition that's often very necessary in order to apply the more advanced techniques of calculus. In this video, we will explore the other most important property, differentiability. In the same way that we learned how to verify that a function is continuous at a point, we will now learn the technique for assessing whether it is differentiable at a point. In so doing, we get to see how intimately connected the two properties are. So without further ado, let's get started. So let's begin with a scenario I've called a tale of two peaks. Sorry, it's a little corny, a play on the tale of two cities, and it's not even that fascinating of a tale, but it's a nice context to think about differentiability. So here we have a mountain peak, so to speak. Oh, that rhymes. Anyway, it's covered in snow, and we have a skier being pulled up by a pulley and reaching the summit and just kind of waiting there for the slopes to clear so they can ski down. Contrast that with this peak here, skier being pulled up at the top, waiting in order to be able to descend. And if I asked you which slope would you prefer to ski on, you might say this one, because if you're into extreme skiing, and myself, I'd prefer the first because I'm not a very good skier. But I wonder if you would say the same thing if you had to wait 15 minutes there. I think if you had to wait 15 minutes or more on the right-hand slope, you might start to find it really hard to balance. So I'd like you to kind of appreciate the difference between the two. I would say that in the first case, the skier is quite stable there and can wait a long time before descending. But in this one, it's I would say the skier is unstable. And how does that translate to derivatives? Well, in the first case, you see that the skis are actually technically also a tangent line there. The tangent line is well defined, and in particular, we can say that f prime equals 0 there. But in the other case, it's not clear where the tangent line is. In fact, because of that, we say that the tangent line, or f prime, does not exist because we cannot sort of pin down what that tangent line would look like. And so in the first case, we say that because f prime equals a number, in this case 0, that the function is differentiable there. But in the second case, because f prime is undefined, the function is not differentiable. And a way to think about it sort of loosely is that if you think about the inclination of the skier as they're approaching the summit, the f prime at any point of f prime is approaching 0 from the left and from the right. So the slope from the left and from the right they're both approaching 0, which is why f prime equals 0 there. In contrast, if we thought that f prime here, maybe f prime is approximately 2 on this side, then by symmetry, f prime would be -2, and they're clearly not approaching the same value. So in that sense, the derivative does not exist. So I'm going to refer to the first one as the smooth peak and the second as the pointy peak. I have those in quotation marks because, well, smooth is a mathematical term, which we'll talk about later. Pointy is not, so please don't use that in your descriptions of calculus moving forward. So let's take a closer look at the calculus behind whether a derivative exists or not. So recall the two formulas for finding the derivative, aka the slope of a function at x equals a. They're not really two different formulas, it's the same formula with different notation. So in the first one, we notice that this quantity, that's the difference quotient. It's really the rate of change, the average rate of change over the interval a to a plus h. And in the second one, we take the average rate of change over the interval a to x, and then we allow x to approach a. We are going to be using this one in this video because the algebra is sometimes simpler and more straightforward when we're evaluating that. So we will be using that moving forward. Now note, the derivative is a limit. So therefore, if you can find an answer to this limit, if it exists, then we can say that f is differentiable at x equals a. But if the limit doesn't exist at x equals a, then f prime of a is said not to exist, and it's not differentiable there. Sometimes with f prime a, though, you have to consider one-sided limits. So to check for certain functions, to check if the limit exists, to check if the function is differentiable, you must consider the one-sided limits. So let's take a look at the calculus of the first peak, the smooth peak. And here I've modeled it with an upside down parabola, and the equation of that parabola is negative x squared plus 4. And we've got to prove that it's differentiable at x equals 0, which in effect is basically proving that we can get an answer for f prime 0. So I'm going to take the definition of the derivative, and I'm just going to replace 0 in for a. And then I'm just going to do the math. So f of x is negative x squared plus 4. And f of 0, well, if we just plug 0 into here, we get 4. That's just the y-intercept, so minus 4. Notice that these cancel. The 4 and 4 cancel. And so we have the limit as x goes to 0 of negative x squared over x. We see that that is really just negative x, so we lose the x from the denominator, it cancels out, and we're left with the fact that that is equal to 0. So we have just proved that the derivative exists at 0, and we've also at the same time said, well, what that means is that there exists a horizontal tangent line whose slope is equal to 0 right there. So f of x equals to negative x squared plus 4 is indeed differentiable at x equals 0. So now we'll turn our attention to the calculus of the pointy peak, which I've modeled with an absolute value, an inverted absolute value function. And we're going to show that it's not differentiable at x equals 0. So we call up the definition of the derivative, and we see here, don't forget that a is replaced with 0. And so we can sort of dive straight in. So f of x is just this. And f of 0, we can see from the graph or the function, is just 4 also. So we do this. These cancel. And we're left with this. Now, you might be tempted to cancel the x in the denominator with the absolute value of x in the numerator, but that's not actually allowed. We need to really look at that absolute value of x because it changes, its definition changes depending on whether x is positive or negative. So we'll take a moment over here and think about how we can release x from the absolute value. And the only way we can do that is to turn it into a piecewise function whose definition changes depending on whether x is positive or negative. So if x is positive, we don't really need the absolute value around it because x is already positive to begin with. But if x is negative, so I can't just take away the absolute value sign, because then if I say the answer, say x was negative 3, and I take away the absolute value sign, I'm basically saying that the answer is negative 3. Well, it's not. It needs to be positive 3, so that has to be replaced with negative x. So now, the only way to evaluate this limit is to consider it from the left and the right. So we'll start with from the right. So as I said up here, if x is positive, approaching 0 from the right, I can just replace absolute value of x with x itself. These cancel, and I'm left with the limit as x goes to 0 from the right of negative 2, which is just negative 2. Now, if I consider it from the left, I can replace absolute value of x this time with negative x. And this, of course, is just positive 2x. These cancel, and I'm left with the limit of positive 2, which, again, there's no x in there, so I just know that the answer is 2. And the critical thing here is that these do not match. The limit from the left and the limit from the right do not match, which means that the derivative doesn't exist at 0, right? So the derivative doesn't exist here, so because there's no tangent line that we can define here. So f prime doesn't exist. And one last thing I'd just like to point out, what the 2 and negative 2 mean, we probably could have figured this out. Well, we should have been able to figure it out without even doing the calculus, because we see that the slope here on this branch is f prime equals 2, and on this branch is f prime equals negative 2. And obviously, there's no way that those derivatives from the left and the right are ever going to match. So in this slide, we're going to take a graphical look at why one of the peaks is differentiable at x equals 0 and the other isn't. And we're going to do it by actually zooming in around x equals 0. So I'm going to take this little rectangle here, I'm going to zoom in, and this is what I get when I zoom in. And then I'm going to repeat this, zoom in there, and we get to this stage, we'll see, just to prove that we've zoomed in, right? The lowest bar here was 3, we went to 3.9, and now we're at 3.99. And you will notice that even though we know it was a quadratic, when we zoom in this far, we can actually see that it really resembles a linear function. In fact, if I sketch the tangent line here, it would be almost indistinguishable from the quadratic function. And that's the concept of, when I called this a smooth function or a smooth peak, that was the kind of, smooth is a very precise mathematical term, but you can think of this, we're using it a little loosely here, of like you're smoothing out the curvature in the function, and therefore the derivative exists, the tangent line exists. In contrast, if I take the same kind of regions for the pointy peak, notice that it kind of looks exactly the same. And if I repeat, ditto. We're not changing with the shape of the peak at all. No matter how much we zoom in, we'll never smooth out that peak. Therefore, it's not differentiable at x equals 0. So in this slide, we're going to identify the sort of 3 cases in which a function is not differentiable. So the first one is really like the situation with the pointy peak. What's good to notice here is that both branches have a slope that's discernible. So this might look like a slope of 2, and this might be a slope of half, but they don't match each other. This has an official term. We're no longer going to call it like a pointy graph, but it's officially called a corner. A corner could also look like this, even though it doesn't quite seem to reveal a corner, if you can determine the slope from the left and the right. So this looks pretty steep. Maybe this is the slope of 5, and this is the slope of -5. Just at that point there, if we can determine the slopes at actual numbers, but they're not equal, then we have the presence of a corner. In contrast, we have something like this. Now this does look like a smooth curve. It doesn't have the pointy bit, but in this situation we have a vertical tangent line. So if I try to draw a tangent line right here, now this is going to defy everything we've known before, because this tangent line actually passes through the curve. And we have always thought that tangent lines should only touch down. But technically at that particular point, let's call this A, we can construct a vertical tangent line. And the reason we think about that is that the tangent if we looked at tangent lines approaching that point, it's getting higher and higher and higher, larger and larger, closer to infinity, and also from the other direction. So I'm going to put there that the slope of that line is infinite, but that therefore the limit doesn't exist, because infinity is not a valid limit. So when we have a vertical tangent line at that, so at A, the curve there is not differentiable. And for another similar situation, it looks different, but it's the same idea. The slope in this direction is approaching -infinity, and in this direction, getting steeper and steeper and steeper. We can't actually determine the slope like we could in the case before of the corner. Once again, you kind of have the vertical tangent line if you go right to the point A. This one situation has a special term. This is called a cusp. Sometimes cusps and corners are confused, but hopefully this clarifies that for a cusp you'd have to have the slope, the tangent line, heading to a slope of infinity or -infinity, whereas in a corner you actually, both branches have a discernible slope. Okay, and the last case is naturally a point of discontinuity. Now, you might say to yourself, well, it certainly appears like the slope approaching from the left and approaching from the right is the same, but the problem is, let's bring up the definition of a derivative. The definition of the derivative, you can't calculate it unless f of a exists. And in this case, f of a doesn't exist, so therefore it's not differentiable at x equals a. And that's obviously a discontinuity, and this would be another example of a discontinuity. So where we wouldn't have a tangent line where it's not differentiable. So here, now technically, if this is a, technically f of a is defined here, but the problem is that f of a, for working out the slope from the left, we'd have to use that f of a. But if we want to determine the slope from the right, we can't be using this value of f of a. To work out the slope from the right, we'd have to actually use the coordinates of that point, which doesn't exist. So we're just going to formalize the definition of differentiability. So we know the definition of a derivative. We know it's a limit statement, but if we really want to see whether a function is differentiable at x equals a, we really need to look at the limit from the left and the right to make sure that they match, and then we can say it's differentiable, aka the derivative exists. Now there's a couple of important, there's a connection between differentiability and continuity that's really important. As we saw in the previous slide, if a function is not continuous at x equals a, then it is not differentiable there. So a logically equivalent statement, if you recall back to geometry, if you learned about a conditional statement and it's contrapositive, they're logically equivalent. To get the contrapositive, you reverse the if-then statement and you negate both statements. So it must follow that if a function is differentiable at x equals a, then it is automatically continuous there. So this is a very important connection between differentiability and continuity, and we will see that this matters as we proceed in the course. So now we have all the tools to investigate whether a function is continuous or differentiable at a point. And it matters because these two properties are very important in order to be able to carry out more advanced analysis as calculus proceeds. So we are going to look at this piecewise function. And we know for piecewise functions that where at x equals 2, in this case, where the definitions change, could be a candidate for a discontinuity and potentially for it not to be differentiable. But let's go ahead and see. So here's the definition of continuity, which says that the limit as x goes to 2 of the function has to exist and also equal the value of the function at 2. So if we break this down, so let's look at the limit from the left of the function, and from the left we will be using this branch when x is less than 2. So we just plug in 2 and we get 3. If we repeat this from the right, then we will be using this branch when x is greater than 2, which would be negative 2 plus 5, which also equals 3. So far so good, the limit actually exists. The last thing we have to check is whether f of 2 is also equal to 3, and if we go to the piecewise function, we see it is. So therefore, we can establish that f is indeed continuous at x equals 2. Now we know continuity does not guarantee that it will be differentiable, so we need to go to this next step, recall up the test for differentiability, and we need to dive right in. So as x approaches 2 from the left, we would be back using this branch here. So that f of x is just going to be x squared minus 1. And we just worked out f of 2 over here. So that's minus 3 over x minus 2. And we can see that this becomes x squared minus 4 over x minus 2. We know that x squared minus 4 factors as x plus 2, x minus 2. The x minus 2's cancel, which makes it safe to plug in 2 into the remaining x plus 2. We get that that's equal to 4. And now we're going to repeat from the right. So from the right, we're going to use negative x plus 5 minus 3 again, all over x minus 2. So from the right, we get, on the top, we get 2 minus x. On the bottom, we have x minus 2. And hopefully, you can recognize that answer as just being negative 1, because 2 minus x and x minus 2 are opposites of each other. Since these do not match, 4 and negative 1 do not match, we conclude that f is not differentiable at x equals 2. So let's just look at a graphical representation of this piecewise function. We'll have a graphical representation of what's going on. So if you, as you can see, the function is indeed continuous at x equals 2, and it's not differentiable. We should recognize that we have a corner there. And if you recall from the previous slide, we found that the derivative from the left was 4, but the derivative from the right was -1, which you can see in the graph. It has a slope of -1. And I just want to practice graphing the derivative. Now that we've been introduced to these points where functions are not differentiable, how do you actually graph the derivative? Well, we know that as we approach 2 from the left, the slope is 4. So we know that it's kind of heading up there. Now we can't really put a dot there because we don't know that the slope is what it is exactly. We do know that it's undefined right at x equals 2 because it's not differentiable. And we know that the slope to the right is -1, so I'm going to put a circle there. In fact, to the right, if you notice this, it's a straight line. Well, all lines are straight, aren't they? But it's a line whose slope is -1, so therefore that looks like graphing the derivative to the right of 2. To the left of 2, I might draw your attention to what we did in a previous video. The slope here, we know that the slope right there is 0 at that minimum. And we maybe at x equals 1, looks like the slope might be +1. So, well, actually could be +2. So let's put it up there. If we continued graphing points estimating, then we would see that the derivative function f prime, that branch, the derivative of the parabola is a linear function. And on the right-hand side, the derivative of a linear function is a constant. So how does the fact that it's not the orange graph, which is f, is not differentiable at x equals 2, we see that the slope from the left and the right is not equal, and also there is a discontinuity in the derivative graph. So let's end by practicing sketching a derivatives when we have points where a function is not differentiable. And if we look, let's start at x equals -1. At -1, it looks like the slope is about -2, so I'm going to put an x there. And this is a parabola, this first function here, so I made the vertex right here at x equals 0, so we can say that the slope from the left is 0. And we have a constant function here, so the slope from the right is 0. Therefore, the derivative exists at x equals 0, and it's actually 0. And we can, if we recall, the derivative of a quadratic is a linear function, so I'm going to just put that roughly in there. Next, we have that this along here, this is also the derivative along here. This constant function is also 0, but we have a little problem at x equals 1. At x equals 1, it seems that the derivative from the left is 0, but the derivative from the right looks to be about, maybe a half. So we're going to have an open circle here because the derivative from the left and the right is not the same. Actually, you should recognize that as a corner. The derivatives from the left and right exist, but they don't match. And so the derivative from the right is a half, and we're going to move on up from there. We can tell that the slope is getting steeper and steeper. In fact, it looks like it's heading up to infinity, and it is because we have a cusp here. So that means that this is, if I'm graphing the derivative function, it's looking like this. So remember, the blue graph is the derivative, the green is the original. And from the left, it's approaching, of x equals 2, it's approaching infinity, and from the right of from the right of 2, the slope is -1, and that's constant of -1 because we have a linear function, so I have to put an open circle at -1, a couple little marks there, and indicate that the derivative there is a constant function. So there we have practiced sketching the derivative of a function when corners and cusps are present. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.